Materials behave in predictable ways. When you stretch a rubber band, it becomes thinner in the middle. This common behavior is described by a property called the Poisson's ratio. Most materials have a positive Poisson's ratio. This means they contract in directions perpendicular to an applied stretching force. Imagine pulling on a piece of clay. As it gets longer, it also gets narrower. This principle applies to nearly everything we interact with daily, from fabrics to metals. It is a fundamental concept in materials science that governs how objects deform under stress. Auxetic metamaterials, however, defy this common intuition entirely. These are highly engineered structures that exhibit a negative Poisson's ratio. This unique characteristic means that when you stretch an auxetic material, it actually becomes thicker in the perpendicular directions. Conversely, when you compress it, it gets thinner. This behavior is not found in most natural materials, but is achieved through carefully designed internal geometries. The term auxetic comes from the Greek word auxetikos, which means that which tends to increase, perfectly describing this strange and useful property. The magic of auxetic materials lies not in their chemical composition, but in their structural design. They are often called metamaterials because their properties arise from their structure rather than their base substance. You could make an auxetic material from polymer, metal, or ceramic. The key is the internal architecture, which features specific repeating patterns. These patterns deform in a special way that leads to the negative Poisson's ratio effect. This counterintuitive expansion and contraction mechanism opens up a new world of possibilities for designing smart materials and functional devices. This unusual property leads to several other enhanced mechanical benefits. Auxetic materials are excellent at absorbing shock and energy. When an object impacts an auxetic surface, the material densifies at the point of impact, drawing material inward to become stronger and more resistant. This is the opposite of conventional materials, which tend to fracture and disperse away from the impact point. Furthermore, they demonstrate high shear stiffness and fracture toughness, making them incredibly resilient. This combination of features makes them highly desirable for applications where durability and protection are paramount. The remarkable properties of auxetic materials are a direct result of their internal structure. One of the most common designs is the reentrant honeycomb. Unlike a typical hexagonal honeycomb where the cell walls bow outwards, a reentrant structure has cell walls that are angled inwards. When this structure is stretched horizontally, the reentrant ribs are forced to hinge outwards. This hinging motion pushes the overall structure to expand vertically as well. This coordinated deformation mechanism is the source of the negative Poisson's ratio, turning a simple pulling force into a two-dimensional expansion. Another fascinating design is the chiral structure. Chiral systems are characterized by their lack of mirror symmetry, much like our left and right hands. In an auxetic context, these structures consist of central nodes, or cylinders, connected by tangential ligaments. When a force is applied, these nodes rotate. This rotation wraps or unwraps the connecting ligaments, causing the entire structure to expand or contract uniformly. The direction of rotation determines whether the material expands or shrinks, and this mechanism allows for a high degree of control over the material's response to stress. Rotating rigid structures offer another pathway to achieving auxetic behavior. These designs are composed of rigid squares or other polygons, connected at their vertices by hinges. When the material is stretched, these rigid polygons rotate relative to each other. This rotation causes the gaps between the polygons to open up, resulting in an overall expansion of the material in all directions. This type of structure is relatively simple to design and fabricate, making it a popular choice for research and practical applications. The degree of auxetic behavior can be finely tuned by changing the shape of the polygons and the arrangement of the hinges. These are just a few examples of the many geometries that can produce auxetic effects. Researchers are constantly exploring new and more complex designs, including three-dimensional versions of these structures and fractal-based patterns. The key principle is always the same: to create a mechanism where tensile strain in one direction induces a transverse expansion rather than a contraction. By manipulating these internal architectures, scientists can create materials with customized mechanical properties tailored for very specific tasks, unlocking performance levels that are impossible to achieve with conventional materials. The unique properties of auxetic materials make them highly valuable in the aerospace industry. Components for aircraft and spacecraft must be lightweight, yet incredibly strong and resistant to impact. Auxetic composites can be used to create panels that are both light and exceptionally good at absorbing energy. If a piece of space debris were to strike a satellite panel made from auxetic material, the panel would become denser at the impact site, effectively self-strengthening to prevent a puncture. This quality also makes them ideal for creating fasteners and rivets that provide a more secure fit when placed under tension. In the medical field, auxetic materials are showing immense promise for developing advanced biomedical devices. For example, their ability to expand when stretched makes them perfect for creating smart bandages. An auxetic bandage could be designed to deliver a controlled amount of a drug as it expands in response to the swelling of a wound. Similarly, they are being explored for use in stents, which are small tubes used to open clogged arteries. An auxetic stent could be easily inserted in a compressed form and then expanded with greater control and a more secure fit against the artery wall. Protective equipment is another area where auxetic materials are set to make a significant impact. Their superior shock absorption capabilities make them ideal for helmets, body armor, and padding for athletes. When an auxetic foam is struck, it becomes harder and denser, providing better protection than conventional foams that simply compress. This means helmets could be made thinner and lighter without sacrificing safety. This technology could drastically reduce the risk of concussions in sports and provide better protection for military and law enforcement personnel in the line of duty. The benefits of auxetic design are also being applied in everyday consumer products. Auxetic textiles could be used to create more comfortable and responsive sportswear that moves with the body. In footwear, auxetic soles could provide superior cushioning and support by adapting to the pressure points of the foot during movement. Even filtration systems can be improved. An auxetic filter could be designed with pores that open when stretched. This would allow for the filter to be easily cleaned by simply stretching it, releasing trapped particles without the need for backflushing or chemical cleaning. The future potential of auxetic metamaterials is vast and exciting. As our understanding of their underlying mechanics grows, so does our ability to design them for increasingly complex tasks. Recent research is focused on creating dynamic auxetic systems that can change their properties on demand. Imagine a material that could switch from having a positive to a negative Poisson's ratio with the application of an electric field or a change in temperature. Such tunable materials could lead to revolutionary new technologies, including soft robotics that can change their shape and stiffness to navigate complex environments. Advancements in manufacturing techniques, particularly three-dimensional printing, are accelerating the development of auxetic materials. Additive manufacturing allows for the creation of intricate internal geometries that would be impossible to produce with traditional methods. This enables researchers to rapidly prototype and test new designs, optimizing them for specific performance characteristics like energy absorption or permeability. As three-dimensional printing becomes more accessible and advanced, we can expect to see custom-designed auxetic components becoming more common in everything from personalized medical implants to high-performance vehicle parts. One of the most promising frontiers for auxetic materials is in large-scale structural engineering. Their ability to resist fracture and shear forces makes them an excellent candidate for building materials in earthquake-prone regions. An auxetic building frame could potentially absorb and dissipate the energy from seismic waves more effectively, preventing catastrophic structural failure. Researchers are also exploring their use in deployable structures for space exploration or disaster relief, such as shelters that can be compactly stored and then easily expanded to a large, stable size on site. In conclusion, auxetic metamaterials represent a paradigm shift in materials science. Their counterintuitive behavior, born from intelligent structural design, provides a powerful toolkit for engineers and innovators. From enhancing personal safety to enabling new medical treatments and creating more resilient infrastructure, the applications are nearly limitless. As research continues to unlock the secrets of these remarkable structures, auxetic materials are poised to move from the laboratory into our daily lives, shaping a future built on materials that are smarter, stronger, and more adaptable than ever before.